Very good morning, one and all. We are learning the subject of the circuit theory or the network analysis. Today we will continue the steady state and the transient response last topic. That is nothing but the Laplace transformation. We have studied in the steady state what is the change, how the sinusoidal series as well as the parallel RLC component plays the role. Even we have seen the changes. We have learned that in the transient responses also, what will be the change with respect to time period, what will happen if the switches are to be closed and the open. So what is the effect of the open circuit as well as the short circuit for the RLC, either the connected in the series or the what you can say the parallel connection. So the last topic related to the steady state as well as the transient response chapter is nothing but the Laplace transformation. This content already you have studied in maths. Okay, so little bit is in the what we can say the network analysis of the circuit theory. So the basic introductory part of the Laplace transformation we will study today here. How that Laplace transformation is converted from the frequency domain to the time domain, or simply how the function will be changed. So in the Laplace transformation, the function is denoted by f of t. Okay, that f of t, that is the time period we are going to be convert, that we are interested in the frequency domain, or time domain is converted into the frequency domain. Just simply we want to observe the function. So how that is going to be changed? See here. So f is the function, you can say, okay, so S is nothing but the complex frequency variable, and that is nothing but we know variable. This is the real as well as the what we can say the imaginary part, that is the conductivity plus G of omega, the angular frequency ranges. Okay, so here we are having the real as well as the imaginary part. Both the things will be available. So if you are going to convert that function, okay, of the frequency into the time domain, okay, so that is possible with the help of that Laplace transformation. And you can convert with the help of this Laplace by taking the integral of that 0 to infinite, and you can convert this f of t. How you can convert this f of t if you are going to be considered in the if you want to convert into the what we can say the Laplace transformation with respect to the time period f of t with the exponential form, that is nothing but e raised to the power minus st dt. Okay, so in short, this integral as well as the derivative part will be useful for converting the Laplace transformation functions, okay, from the one domain to the another domain. So here we need to take care about the limits. That limits may be from the 0 to 0 minus to the 0 plus. Okay, that initial or you can say the final limits are there. So in this way, the function is nothing but my f of t that must satisfy all the conditions of the Laplace transformation. How it is possible to satisfy that condition, that is listed here, that we need carefully, we should study and we should know what are the things, how we are going to be convert from the one domain to the another domain. Okay, if you are taking the initial and if you are applying the initial and the final condition, just like you are from the 0 minus to the 0 plus, or from the 0 to the infinite value. Okay, how I can substitute the value of the Laplace of the f of t, how I can convert my e raised to the power. So see here, if s is a complex frequency variable, so this s is nothing but the conductivity sigma. This notation is a sigma plus j of omega. How I can convert that one, e raised to the power of this conductivity with respect to the dt less than the infinity. So in this case, but this should be in the standard form. Whatever we are having the variable, okay, whatever we are having the variable of s, that we should convert into the standard form. How we can convert that f of s, this s, that we can convert into the f of s. This f of s will be going to the Laplace of f of t, and that will be converted into the integral form as well as in the what we can say the derivative form. So later on you need to convert into that function with respect to time period along with the exponential form function, that is nothing but e raised to the power of so and so. Getting? So that we should keep in your mind, and how we are going to apply the limit, how we are taking the initial and the final condition, whether they are greater than and less than the differential time, that we need to take care. In this way, we should study about the what we say the Laplace function. You can say Laplace transformation. Okay, So here we know very well this conductivity is nothing, conductivity plus j of omega. Conductivity is a real term, whereas j omega is nothing but here the imaginary part, angular frequency. So here the conductivity is the real and the positive, okay, real as well as the positive. While you are going to take the inverse Laplace that time, so L is denoted as a Laplace transform. Okay, so if we are taking inverse of that, that is nothing but -1. Already you are aware from all these basics in the maths, already you have studied, just overlook is here. So this inverse of Laplace is nothing but L of -1, and what we are doing inverse of that, the S variable complex, that is converted into the f of s. Okay, so again that f of s will be converted into the f of, how it is in the inverse form, that's we are interested to convert this part. Okay, we are interested to convert this part. So in the time domain, so f of t is equals to omega. There's 2 pi f. We are aware from that 2 pi f. Okay, we are taking in the with respect to the time period, or with respect to the angular frequency. So 1 by 2 pi, instead of taking that as a g will be there. Okay, and we are applying the limit conductivity plus j of infinite, because the limit are 0 minus to the infinity. So that's why plus or minus conductivity plus or minus of j of infinite. And this symbol, that is f of s. Okay, this f of s e raised to the power st ds. Okay, all these things are we are taking in the inverse. If you observe same thing in the only the Laplace transform, here was e raised to the power minus st into dt. But here this is the inverse Laplace. So same the with respect to t will be converted into the with respect to the s domain. Okay, either the s will be converted into the f of s, then the into the f of t, or vice versa, that is f of t will be converted into the f of s, then the s. Likewise, because in Laplace transform and inverse Laplace transform. Okay, so likewise, we should, there are a few important functions are related to this Laplace transformation. The how we are getting the waveform. It's not necessary every time we are getting the sinusoidal waveform. The waveforms are in a very different modes, very different types. So if we are talking about the conversion or the transformation from the time domain to frequency and the frequency to time domain, by using the various function, you can transform each and everything with respect to the time period. So each, even by applying the integral and the differential form, that is possible. So we need to observe all the waveform, that is from the sinusoidal and the non-sinusoidal waveforms. And we should remember the condition, how we can apply that things, how we can convert into the Laplace, how we can convert into the inverse Laplace. So one of the waveform is mentioned here in the Laplace transformation, that is nothing but unit step function. Okay, one of the function is nothing but unit step, the waveform which is in the, what we can say, the which is happening in the zero, acting in the 0 to 1 or in the constant way. There is no as such change in the, if you observe the non-sinusoidal waveform, you can say from the 0 to 1, just like a digital form. So that is nothing but the unit function. And that unit function, how we can write? So we can write either in terms of the 0 or we can write in terms of the 1. So see that u is denoted by the unit step. Okay, with respect to the time period, that's why u of t either the 0 or the 1. Whenever you are getting that unit is 1 from increasing from 0 to 1, that definitely t will be greater than the 0. And whenever you are having the 0, so t will be lesser than the 0. And the same for the same waveform, if we want to apply the, what you can say, the transformation or Laplace transformation at the time, how you can convert that one? So L is nothing but Laplace of u of t. Okay, it will be equals to 0 minus, that is before switching. Okay, before initial, that is a 0 minus up to the infinite. That's why integral of 0 minus to infinite u of t of e raised to the power minus st dt. See here, if I'm interested in the Laplace of the time domain, so here will be the dt form. Okay, inverse Laplace ds form. See here the difference between these two. Okay, getting? So L of u of t is equals to integral of 0 minus infinite u of t, which is minus 16 to dt. Likewise, you can convert later on again that u of t is, you can substitute the value of u of t. So u of t at the 1 position, when the t is greater than the 0, at the time we can substitute the value of u of t is nothing but the 1. E raised to the power minus t will be as it is, the dt will be as it is, and then apply the limit of that 1 dot of e raised to the power minus st dt. So what will happen here? The integral of e raised to the power minus st. So what will happen after applying that integral, converting that? So e minus will be at one side. That you should aware from all the integral and derivative parts with the help of the maths and other things. So you should aware. Okay, so you should know how we can apply the limit, how we can do it, the derivative part. Okay, that is not the rule here, how we are going to convert. You should aware from that. So integral of 0 minus to infinite e raised to the power minus st will become as minus will be at one side. Okay, and e raised to 1 minus st divided by s will be there, and we are applying the 0 minus to infinity, the entire limit. Okay. Now the second is nothing but if there is a delay in the same waveform, that is nothing but the unit function or a unit step function. See here the delay, that is nothing but the instead of starting that from the 0 to 1, it's taking a time of up to the a. We don't know exact time, but we are aware the time delay is nothing but that 0 to a. Few amount is going to be delayed. So how much amount going to be delayed, that you should mention here. So here is a 0 with respect to t. So u of t is nothing but minus of a, means up to the a we are getting the delay. So that the delay is nothing but either called as the delayed or the shifted unit step function. So here t minus of a, how much amount of delay, total time period is a t, from 0 to up to t is a total time period, and how much amount of a delay is going on. So in this way you can find the particular the time from there the waveform is going to be start. So here in this way you can find, so here will be again 0 to 1 and the t is greater than the a and t will be less than instead of zeros. So here we are not interested in the 0 because so we are far away from the 0, that the delay is already occurred and we are concentrating from the a part. So that's why the t must be greater than the 0 if the 1 is there and t is less than the 0 like this. And if you want to do the Laplace transformation of this delayed or the shifted form, so u of t minus of a is possible. See here, at the place of u of t, you just take the u of t minus of a and apply the limit here. Instead of 0, we are starting from the a point just because of the delay. So a of infinite, again here u of t minus of a, we are substituting the value that is nothing but the 1 e raised to power minus st dt. Again, just apply the limit here. So minus of this one will become at the one side a raised to 1 st divided by a and applying the limit of a to infinite. So you can substitute at the place of what we can say s value, you can substitute the infinite. Okay, infinity. In this way, the next function is nothing but our next waveform is nothing but the unit ramp function. So it's look like the linear function. So see here how it's going as a straight line. So r is denoted as a ramp function. So the r of t with respect to time period t, and it will be the linear form. Same. So r of t at t, because it's a starting from the 0. So r of t at a particular t is greater than 0 and 0 whenever it's a 0 at a particular instant 0. Okay. So at that time t will be less than this 0. How we can apply the Laplace r of t? That is again the 0 minus of infinite. So r of t e raised to power minus t into dt. So here in this way, if you are going to apply that limit of 0 minus to infinite, so r of t is nothing but my t. How I am taking my t? Because it's going straight, and it's, if you are going to take here at any particular moment, so it will give you a t only. Okay, so that's why this t dot e raised to the power minus st dt. So this t into e raised to the power minus st dt will be converted after applying the limits. So t is the constant of, okay, so that will be converted and you will get in terms of the s, that is nothing but 1 by s square. 1 by s square. Next is nothing again the delay will happen with the a part. See here there's a, whenever you are having the t with the minus of a, it's a delay. You can substitute the value at the place of r of t. You can substitute the t minus of a, then the t and the 0, t is greater than the a, t is less than the a. So in this way you can apply again the Laplace of delayed or the shifted unit ramp functions. You can apply the limit of a to infinite. So t raised to minus dt. So here will be at the place of what we can say, you can apply what we can say t square by 2 or likewise. Okay, if you're taking the t as a constant and you are applying the integral of e raised to power minus st, so you look it as e raised to power minus, at the place of s you can substitute the value for at the place of t you can substitute the value of u of the a, e raised to power minus a is divided by s square. Next is nothing but the inverse, which is starting from the 0 of the same what is the phase. So that is nothing but the unit impulse function, and here will be denoted by the del of t with respect to t. So del of t will be either the zeros or directly the 1. So here if del of t at particular instant, which is going to start from 0, so that time t is not equals to 0. T is not equals to 0 because at this moment is a 0 as well as the 1. So we can't conclude that this t is equals to 0. So it's a t is not equals to 0, and whenever you are applying the limit, here should be Instead of 0 minus, here will be minus infinite to infinite. So del of t of dt, which is equals to 1. Whenever you are having the t is equals to 0. If t is equals to 0, then only it will be treated as a 1. Otherwise, it will not be, t is not equals to 0. So in this way, you can apply the Laplace to the, what we can say, the unit impulse functions, integral of 0 to infinite, del of t raised to the power minus st dt, that will be equals to 1. Similarly, same you can apply 0 minus e raised to the power minus s minus of e of t. So again, this minus will come outside, e raised to the power minus s minus of e of t divided by s minus of e, 0 minus to infinite. So this will be entirely converted by 1 by s of s minus of e. So next is nothing but here the omega t, the function omega t. Whenever you are having omega t, so that will be 1 j of e raised to the power j omega t minus of e raised to the power minus j omega t. So these are the exponential form, how we can write the expression if whenever you are having the omega t. Whenever you are having the omega t, you can convert that omega t while you are going to transfer from the Laplace any s function into the Laplace with respect to the time period. So you can write in this way. You can write in this way. Okay, how you can convert in this way in the exponential form 1 by 2j e raised to the power j omega t, because ultimate omega is nothing but again the 2 pi f. This f is nothing but again the 1 by t, say tt will be cancelled out. Okay, so this 2 pi will be there. Okay, so this will Laplace of sine of omega t. You can take that L of again L is nothing but the Laplace of that in the bracket 1 by same value will be there omega t, sine of omega t. So L will be there in bracket sine of entire expression, that is a e raised to power j omega t omega 2 pi f. F is a 1 by t. T will be cancelled out. That's why we are writing the expression like this. Secondly is nothing how you can write the cosine expression. That is important whenever you are having omega t, and if you are writing previous was a sine function and this is the cosine function. So if you are writing for the sine omega t, previous slide was the expression. If you are having the cosine function, that is a cos of omega t. So how you can write that is 1 by p raised to the power same. These are the same. Laplace of cos of omega t, L will be outside. Here instead of that 1 by 2 raised to the power will be as it is. So 1 by 2 will be take outside. Individually you can apply the Laplace of this e raised to the power j omega t again plus of L of e raised to the power minus j omega t. So 1 by 2 will be as it is e raised to the power j omega t. How I can write in terms of the what you can say, this is in the time domain and you can convert into the what you can say the frequency domain, that is 1 by s minus of j omega. See here the j omega t. So 1 by s minus of j omega. Okay, plus 1 by minus minus will become as a plus. That's why s plus j of omega. So finally, if you simplify this expression and cross multiplication, you will be able to find s by s square plus omega square. So the next function is nothing but the damped function. Okay, so damping, I mean, might be you have heard in the oscillating, over damping and under damped. So in such a case, in such a what you can say the waveforms, in that case, how we can apply the transformation of the Laplace, how we can simplify the exponentially damped function if you are having the exponential just like your a raised to the power minus 80 of t. So here, if you are going to apply then the Laplace to the particular that damped function e raised to the power minus 80 of your the f of t for dt, so 0 to infinite, that is f of t e raised to power 80 e raised to the power minus st after substituting value. See here, this one is exponential form, this one is a f of t of form. Okay, and you are applying and you are multiplying with e raised to power. So at that time, so 0 minus integral of 0 minus infinite f of t raised to the power minus, substitute, take it common, which is the common, that is nothing but the t is the common. So s minus minus will become as a plus. So s plus of a of t dt. So after converting this, the applying the limit and the converting this time domain into the frequency, you will get as f of s plus of a. F of s plus of a. Then later on, just substitute whenever you are doing the transformation of the function e raised to the power minus what we can say the f of t obtained by putting the s plus a. How we are putting the s plus a? Just because of by getting the in this case s plus of a. Okay, substitute the value. What is the possibility? Whenever you are having the sine and the cosine, if Laplace of e raised to the power 80 sine omega t is there, the final function will be omega divided by s plus a of bracket of square plus omega square. See the difference. And whenever you are having the cosine function, and if you want to convert into the Laplace, so s plus a divided by s plus a of whole square plus omega square will be the case. So these are the functions every time we are going to change. So ensure the summary of this one is nothing but your the Laplace transformation. Okay. So in the serial number is mentioned and the f of t is also mentioned. The f of t is arranging here. So how we can confirm that you should know. So what is going on? The f of t we are converting into the f of s. The f of s we are converting into the f of t. So in short, time domain is converted into the frequency. Frequency domain is converted into the time domain. Whenever you are applying the time domain into the frequency, that is nothing but the Laplace transformation. Whenever you are going for the frequency to the time, that is the inverse Laplace transformation. So if you are having the f of t, how you can convert into the frequency, that is f of s, the 0 minus of infinity f of t e raised to the power minus s t dt. Likewise, and if you are having two constants and the two frequencies, so at that time a f1 of t and b f2 of t, at that time also a is the constant, and this f1 with respect to time period will be converted into the f1, small f1 will be converted into the capital f1, and this t will be converted into the s. So be simple, keep remember that t is in the time domain, s is in the frequency domain. Okay, and this is a complex variable s, which is equals to s is equals to conductivity plus j of omega. Be remembered. So here f1, so f1 capital F1, t will be s. So same thing, same expression, only the change in the small and the capital for the better understanding, as well as the time domain converted with the frequency denoted by the s. Similarly, in the third case, if there is a delayed or shifted form in any waveform, so how we can write that thing if we are having the a function of a delayed, so and that the waveform is a unit step. So how we can write that is that you should know. This is the function with a delayed or shifted of a which waveform, that is a unit step. That's why we written here like this. So how we can convert that into the frequency? The entire term, which is a function as well as the unit step, can be converted into e raised to the power as. A will be the common. See, in the both the brackets, a is there. T converted into the s. So e raised to the power minus as. How this f of f will be converted into the capital F, and the time domain converted into the frequency. Similarly, if you're having a raised to power minus AT, so here capital F will be there instead of small, and this you can write in the frequency domain, that is nothing but s plus of minus minus will become a plus of a, s plus of a. D by dt of f of t, that is converted into the frequency small s f of s minus f of 0. If you are applying the 0 minus to be 1 by s will be there, converted this frequency domain into the time domain. This is f of t of dt is nothing but f of s. This expression most widely used with the sixth, the first, the second, and the sixth. Most widely used in the numerical value. We are going to simplify the numerical. You should know how directly we are going to convert this limits, how we are applying the derivative form, how we are going to convert into the frequency domain. This f of t becomes as f of s, and this integral and the dt will become as a 1 by s. Similarly, small t is nothing but 1 by s square. Whenever you are having the time domain and that in the t present representation, so that will be converted into the frequency, that is nothing but 1 by s square. Similarly, if you are having the t raised to n, we don't know the power. So at the time, so t raised to n is nothing but the any power. So that will be the n divided by s of n plus of 1. So like this. So second, also we need to remember all these things. The time domain to the frequency domain, the small t to f of t, so minus d by dt of f of s, 1 by small t f of t, that is integral of s of infinite, f of s into ds. So same thing, f of a of t, how will that converted into 1 by f of s by a, u of t unit step, 1 by s, unit step, directly unit step, no delay. So 1 by s. If delayed, this is the unit step, this is the delayed unit step. So u is the unit, okay, 1 by s, e raised to power minus a is divided by s, r of t is nothing but 1 by r s square. So this is the ramp and delayed ramp. So r of t is 1 by s square. Delayed ramp is nothing but a raised to power minus as. So see here in the unit is the s, in the ramp is the square. Whereas in the what we can say impulse, that is a del of t, that is nothing but 1, and delayed is nothing but e raised to power minus s. E raised to power 8 is nothing but 1 by s minus of e. Sin omega t, omega y square plus omega square. Cosine is s by square plus omega square. Likewise, the last expression, whenever we are having e raised to the power multiplied with the sine and the cosine, we will get as omega divided by 2 brackets. So in this way, we can simplify what we can say, by remembering all these things, by simplifying, by converting, by transforming from the one phase to the another phase, you should remember all these things, and that why we required all these things just to apply in the real time to simplify the numerical, also to simplify the to avoid, or you can say to simplify the complex problems. That's why we are learning this Laplace transformation for converting from the time domain to the frequency domain. So how we can apply, that is so important. So we can apply with the help of the circuitry, that is nothing but along with your the RLC, we are applying the sources, that is the voltage source as well as the current source. So if so what will be the effect of that if we are having the individual R, individual L, individual C, or you can say the simply purely R is connected with the source, purely inductor is connected with the source, purely capacitor is connected. So what will be the effect that we can observe easily? Okay, so that is nothing but transformed circuitry. See, a transform circuitry is here. Individually, this is a pure R. Okay, pure R is connected with the source. That source is nothing but the voltage source, and the current is nothing but the I. So voltage is with respect to T, and the current is also with respect to T. Plus or minus the voltage is applied here, and the current is started flow. R is the here. Now this R will be converted into the this time domain is converted into frequency, or from one form is converted into the second. So that is a voltage current relationship in the network can also be represented in the time domain. So here the VI relationship in the time domain, that is V of t. V of t, V is equals to IR. So V of t converted into the by with the help of the Ohm's law, that is the IR. I is nothing but the I of t, and the capital R is nothing but the pure register. How we can convert into the frequency domain? See here the difference. See here the difference. V of t is in the time domain. So V is equals to IR, I of t into R. How we can convert it with the frequency? V of S, t become as R will be as it is. Small I will become as a capital I, small t is become as a S, that is in the frequency domain. Same thing here, V of t will be V of S, I of t will be I of S, R will be as it is. Likewise, you can convert this individual R. Similarly, how the inductor and other capacitor can be converted. If the VI relationship in the time domain, that is V of t, if the voltage is applied across the inductor, so inductor is the coil, and voltage is across that inductor, and the current is started flow from here to plus or minus V of t. I is the current which is flowing. The current will start to flow in the coil. So here will be the before switching, that is a 0 minus, I of 0 minus. So what will be the case? V of t L into d by dt. So this V of t will be, if I want to write this expression in terms of the current, so I is equals to, see here, I is equals to this L will become in the denominator. So 1 by L integral of 0 minus 2t, and this vt will be as it is, and we are applying the dt, and we are taking in the 0 minus plus of I of 0 minus. This transforming equation, how we can write this V of t into the V of s, I of t into the I of s. See here, this is equation number 1, equation number 2. So this equation number 1 will become as a V of s. This is equation number 2 become as a I of s. Or we can write L will become as a L of s. This di by dt will become as a I of s minus of L into I of 0 minus. Because twice the current is there at initially, and second is at 0 minus. Because integral of 0 minus as well as the t. For the t, that will be converted into the s. For the 0 minus, this will be the as it is. We remember this integral part. So we need to apply the twice, initial and the final. So this term is what you can say, the final system is the initial term. So the L of S of I of S, L of I of 0 minus. Similarly, I of S, 1 by L of S will be there, and V of t will be converted into V of S, I of 0 minus divided by S in this way. How we can convert this inductor? You can observe here, that is nothing but along with your the inductor, there will be the current source. Okay. And here in the series and here in the parallel, how you can convert that inductor value in the time domain to the frequency domain. See here, this is in the time domain, this is also in the time domain, and this is also into the frequency domain. These two are in the frequency domain, and this one is in the time domain. So likewise, the capacitor is the relationship between the capacitor, the V and the I in the time domain. How we can write V of t and I of t, the expression for the voltage and expression for the current in the time domain. Same, this time domain can be converted into the frequency domain. Okay, time domain can be converted into the frequency domain. Then only it is possible to show the relationship between the V and the I. So V of t, or we can write this is the vice versa case with the inductor. So this is the capacitor, voltage, current, same thing here. The capacitor C will become as a 1 by a C of S. How it is possible? C 1 by C integral of 0 minus of t I of t dt plus. Here we are instead of the current, we are interested in the voltages, that is a V of 0 minus. Similarly, I of t can be written as a C into dv by dt. Same expression convert into the time frequency domain, that is V of t will become as V of S 1 by C of S. This I of t will become as I of S. This V0 minus will become as a V0 minus divided by S. Similarly, I of S is here, C of S of V of S will be here, and this dv by dt is nothing but C into V of initial and the final. These two are the initial and the final, that is 0 minus and the final. So like this. Now the combination of your RF, RC and RLC, if these three circuits are there which are in the transformed circuitry, okay, which we have converted. Okay, how we can convert with the help of the switches and all. See here, the inductor and resistor and inductor circuitry is there, RL circuitry is there. Voltage is applied, R and L with the help of the switch. The current is start to flow. Depending upon the switch, whether the switch is open or closed, the current will be start to flow in the closed circuitry. So at present, the switch is open, the R and the L is there. Okay, whenever the switch will be closed, then only the effect will happen. We can convert the time domain into the frequency domain. So once the switch is closed, see here the observation. Once the switch is closed, so V, then R and then V, R, L, along with the current. The current IoT will become as a IFS. This V will become as a V by S. See here the difference V by S, R V as it is. L will become as a L of S, LS, IFS. Likewise. So for the t is greater than 0 means time is gradually increases after the switch is closed. So the time is increasing and we are doing the transformation or transform network we can find by applying the cable to the mesh analysis. So here V minus IR is equals to 0, or you can say V is equals to IR. V is equals to IR. So what is that IR? Two cases are here. Inductor is along with that. So you need to take care about the inductor as well as the register value. While you are taking V is equals to IR for the register and the L for the inductor, IXL, like this. So V become as a V by S and IR, so I of T will become as a IFS and R will be as it is for the inductor L of S into IFS. Just take it as it is common IFS one side, you will get as V by L will become in the denominator of that, and this if you are taking the common term here, so this is the adjustment how we can get in this standard equation, that is too important here. So how we got from the V by S, so with this V we are taking this L is at the denominator and this we are taken as the again in the denominator, and we have tried to convert in the standard equation by writing this expression as S plus R by L, because this is R and twice we are multiplying, then only it is possible R by L. Okay, so S plus R by L, because e raised to the power minus R by L will become. So here, if you want to simplify with the help of the mathematical expression, already you have done in the maths. So this IFS, how we can convert this, and here will be the vectors form or the any parameters or the value for the A and the B. This is the A, that is nothing but the A by S, and this is the what is the B, that is the S plus. A by S is this one, A by S, because two sections are there. One is S, one is nothing but S plus R by L. So A by S is one and B by S plus R by L. So in this way, these are nothing but the you are the IFS. That is nothing but the entire expression which we are going to convert is nothing but the partial fraction expansion. Partial fraction expansion. You can do it. Then take is A at one side, S of I of S. This will multiply with the I of S, and inverse S nothing is there means S will be equals to 0. We can treat. Whenever you are having this, substitute value of S is nothing but 0. So this will be equals to 0. Substitute value of S is 0. So S into just cross multiply this, S will be multiplied with this expression divided by this all. So S into this one, S into V by L divided by this will be as it is. So if you are going to substitute this by doing the partial fraction expansion, S is equals to 0. So final by getting the S is equals to 0, we'll get V by R. Similarly, B is equals to S plus R by L of second, this one, S plus R by L of I of S. So here S is equals to minus K R by L minus R by L. So likewise, just to cross multiply this S plus R by L will be multiplied with B by L, and this two will be same as it is. Substitute value of S is equals to minus R by L. Finally, you will get minus V by R. Now just these two values, the value of A, the value of B, substitute in the equation of this one I of S. If you are going to substitute, you will get this expression, and by taking, you can take what you can say, by taking the inverse Laplace. This we have done in the IFS is done, but inverse Laplace, that is nothing but this is in the frequency domain. Now convert into the time domain, that is IFT. So here become as a V by R will be as it is. This V by R will be as it is. Minus of V by R e raised to the power minus R by of t. So likewise, you can convert into the frequency domain and the time domain. Okay. So whenever again this, if you are having the capacitor, the resistor is connected with the capacitor will, instead of Ls, if inductor is there, Ls, if capacitor is there, 1 by Cs. So see here the time is increasing gradually, and with t is greater than the 0, the transform circuit is possible.